Lesson 10, the special role of zero in factoring. So, find all real solutions to the given equations. Number 1, x minus 5 times 3x plus 2 times x plus 3 equals 0. So, when I want to solve a polynomial equation, I want to use the zero product property once that polynomial is in factored form. So number 1, this polynomial is clearly in factored form, and the zero product property says if I multiply a bunch of quantities together and get 0, I know that term is 0, that term is 0, you write that right, 3x plus 2 is 0, or x plus 3 is 0. That's the zero product property, saying if I multiply terms together, if I multiply the factors together and I get 0, one of the factors had to be 0. So we get x equals 5, subtract 2 and divide by 3. So x equals negative 2/3, and x equals negative 3. So the solutions to that equation are x equals 5, x equals negative 2/3, and x equals negative 3. Number 2, 4x squared minus 9 times x to the fourth minus 16 equals 0. So you could apply the zero product property right now, but hopefully you notice that those two terms aren't factored completely. That's 2x plus 3, 2x minus 3, times x squared minus 4 times x squared plus 4 equals 0. But again, that's the difference of perfect squares. I can factor it. So, factored completely, this expression is equivalent to the one I just wrote. Notice that I can't factor the sum of perfect squares there. It can't be factored. So we apply the zero product property and say x equals negative 3 halves, x equals 3 halves, x equals negative 2, x equals 2. And now let's look at this. X squared plus 4 equals 0. That says x squared equals negative 4. What number squared gives me negative 4? Well, if I take the square root, I get x equals plus or minus the square root of negative 4. That is not a real number. We do not have a number whose square root is negative 4. So the x squared plus 4 factor contributes no real solutions. So this equation only has 4 real solutions. Plus or minus, you might see this written as plus or minus 3 over 2, and x equals plus or minus 2. Number 3. So, remember our goal when we solve polynomial equations is to get it equal to 0, which this already is, express it as factors, express it in factored form so that we can use the zero product property and then solve. Well, this is not in factored form, so let's factor it. Always look for a GCF. I can take out a 3x. I'm left with 2x squared minus 9x minus 5 equals 0. Okay, well that's a trinomial with a leading coefficient that's not 1, so we need to use the AC method. What multiplies to negative 10? 2 times negative 5, that adds to negative 9. Well, that's negative 10 and negative 1. So 2x squared minus 10x minus 1x minus 5, those two are equivalent. Factor out a 2x, factor out a negative 1. Oh, they both have a factor of x minus 5, so let me undistribute that. And great. So, in factored form, this is 3x times x minus 5 times 2x minus 1 equals 0. Now that it's in factored form, we can apply the zero product property. That thing's 0, 3x equals 0, x minus 5 is 0, or 2x minus 1 equals 0, and we get, well, 3x equals 0, that means x equals 0. We get x equals 5, add the 1, divide by 2, and we get x equals 1/2. If you need to go through and do the steps for the 2x minus 1, that's perfectly fine. Number 4, determine all real zeros and state their multiplicities for the function below. So I want to find the zeros, so I'm going to set it equal to 0. When we solve polynomial equations, I want it set equal to 0, and I want it in factored form. Well, I could apply the zero product property right now, or I can say, I'm going to factor these expressions some more. That's the difference of perfect squares, and I'm going to clearly have to do some grouping here. So Take out an x squared from the first two terms, and I'm left with x plus 4. Take out a minus 16 from those two terms, and I'm left with x plus 4. Good, because the common factor, 0 equals x minus 4, x plus 4. The common factor there is an x plus 4 term, x squared minus 16. Great, that's the difference of perfect squares. So I can factor that again as x plus 4, x minus 4. Now we can apply the zero product property and say if I multiply a bunch of terms together and I get 0, one of them has to be 0. But how many x? I have x to the 4th squared. I'm just going to simplify this a little bit so it looks nicer. Cubed. So I have 2 factors of x minus 4 and 3 factors of x plus 4. So I get x minus 4 equals 0, or x plus 4 equals 0. So my factors are x equals 4, my zeros are x equals 4, and x equals negative 4. But x equals 4 is a double 0, it's a double root, so that has multiplicity of 2. And x equals negative 4, there were 3 factors of that, so that has multiplicity 3. Multiplicity just means how many times is it a 0. I had 2 of them, I had a repeated factor, so I have a 2, that has a multiplicity of 2. I had 3 factors of x plus 4, which means x equals negative 4, has multiplicity 3. Number 5, write 2 different polynomial functions that have a 0 at 2 of multiplicity 5 and a 0 at negative 4 of multiplicity 3. So we can write p of x. I want it to have a 0 at 2. Well, if x equals 2 is a 0, what's the factor? X minus 2 is the factor. So I'm going to write x minus 2, and I want that to have a multiplicity of 5, so I'm going to raise it to the 5th power. And a 0 at x equals negative 4. Well, if x equals negative 4 is the 0, what's the factor? Well, x plus 4 was the factor. Times x plus 4 to the 3rd. So, great, that's one function that has that, that has those zeros. Let's write another function that also has those zeros. So I'm still going to need this basic structure. But what I can do is I can change the leading coefficient. I can say this has a leading coefficient of negative 3. Could you have picked any number? Any non-zero number? Yes. Or, if you wanted to be sneaky, you could have said, well, I'm going to add in something like x squared plus 1, because we know that that doesn't have any zeros, any real zeros. So this function also has those zeros. Explain your reasoning. We just use the factor 0 theorem. We use the factor 0 theorem to say if x equals 2 is a factor, then x minus 2 had to be the, x equals 2 is the 0, x minus 2 had to be the factor. So really any combination here, the key thing is we have to remember, just because we have a function that has given zeros, there's not just one of them, there's infinitely many, because you can change the leading coefficient, or you could add in these irreducible quadratic terms that don't have any real solutions. Number 6, suppose we know that x plus 2 is a factor of p of x. Explain how we can find the other linear factors of p, find the other factors of p, and use them to determine when p of x equals 0. So, I know x plus 2 is a factor of p of x here. What that means is that something times x plus 2 gives me that cubic polynomial. Well, how do I find that something? I'm going to divide. So, let's divide 4x to the 3rd plus 12x squared plus 5x minus 6 by x plus 2. Could you do this with reverse tabular? Absolutely. Go through, do the long division. Hopefully long division is still in your mind. Hopefully you haven't forgotten how to long divide. What times x gives me 4x squared? Well, plus 4x. 4x times x is 4x squared. 4x times 2 is plus 8x. But I subtract to change the signs. I change the signs to subtract. We get negative 3x minus 6. What times x is negative 3x? Negative 3. This looks good because when I change the signs, I get 0. So I know that I can write 4x to the 3rd plus 12x squared plus 5x minus 6 as x plus 2 times 4x squared plus 4x minus 3. So I found p of x as a linear times a quadratic factor, but I want it as the product of three linear factors because it's a cubic polynomial. So let's take that quadratic and factor it. Let's go over here to the side. 4x squared plus 4x minus 3. My leading coefficient's not 1, so we need to do AC method. What multiplies to negative 12 that adds to 4? What are the factors of negative 12 that add to 4? That's going to be 6 and negative 2. So we go through, split that middle term as plus 6x minus 2x minus 3. Factor out my GCF. 2x plus 3, factor out a negative 1, 2x plus 3. So I know that 2x plus 3 times 2x minus 1 is equivalent to that trinomial. Therefore, p of x can be written as x plus 2 times 2x plus 3 times 2x minus 1. This is a huge idea in this course of I can take a polynomial, I can divide it by one of its factors to rewrite it in factored form, and then I can keep factoring it from there. We found the other factors and used them to determine when p of x equals 0. So I want to know when it equals 0. Well, luckily it's already in factored form, and to solve a polynomial equation, we want it in factored form so we can apply the zero product property. Either x plus 2 equals 0, 2x plus 3 equals 0, or 2x minus 1 equals 0. Then we get x equals negative 2, x equals minus 3, so 2x equals negative 3. So negative 3 over 2 equals x. Add the 1, divide by 2, and x equals a half. So our three solutions to p of x equals 0 are x equals negative 2, x equals negative 3 halves, and x equals 1 half. 7. Factor this expression completely. So this is one of those, I look at it and I get frightened, but I'm not going to freak out because I notice that it's really a quadratic. It's something squared minus 14 times something minus 15. It's something squared minus 14 times that same thing minus 15. Well, I know how to factor this. That's n minus 15 times n plus 1. But I don't have an n. I have this problem with this x squared minus 2x, so let's substitute that back in. X squared minus 2x minus 15 times x squared minus 2x plus 1. So now we need to ask ourselves, can I factor these trinomials anymore? And the answer is yes. Luckily, they're leading coefficients of 1, so you could go through and do the AC method, or you can save yourself some time. What multiplies to negative 15 that adds to negative 2? That's minus 5 and plus 3. And what multiplies to 1 that adds to negative 2? That's negative 1 and negative 1. So factored completely, that expression up there is really the same thing as the product of those four linear terms. They look different, but they have the same value. Question 8, factor this completely. Well, this looks like a trinomial, but it's not an x squared, it's an x to the fourth. My leading coefficient's 1, so I don't need to worry about that, and I know x squared times x squared gives me x to the fourth. So what multiplies to negative 7 that adds to 6? Well, that's positive 7 and negative 1. Is that factored completely? No, because x squared minus 1 is the difference of perfect squares. So x plus 1 times x minus 1 times x squared plus 7. I can't factor that quadratic anymore. And that's it. So always look out. It's a trinomial. It's probably going to be some kind of quadratic. This time it was a quadratic in terms of x squared, not just plain old x. Number 9, find the average rate of change of f of x over the interval negative 1 to 3. So the key thing here is average rate of change. Average rate of change is just a fancy word for slope. Find the slope between over this interval for that function. Well, it's not a linear function, so it doesn't really have a slope, but we can still apply the idea. We'll find the y values for the points, f of 3 minus f of negative 1. We'll find the change in y over the change in x. The x, how do I know those? I want to use 3 and negative 1. Those are the values they gave me on my interval. So we need to find f of 3, which means pick up a 3 and plug it in for x. So minus 9, because 3 squared is 9, plus 24 plus 9. So f of 3 is 24. F of negative 1, f of negative 1 is negative 1 squared is 1, so negative 1 minus 8 plus 9, which gives me 0. So now we just plug it into the formula. 24 minus 0 over 4. So my average rate of change is 6. The slope of the line connecting the 2 points, negative 1 and 3, of that parabola there has a slope of 6. It's the average rate of change. Average rate of change really is just the slope. 10. If f of x equals 4x minus 2, and g of x is a half x squared minus 3x plus 1, express f of x times g of x in standard form. So what I really need to do here is just multiply these two functions together. I want to do f of x times g of x. So even though they're functions, we can still multiply them together. So it's really just polynomial multiplication. You could use a table, great, or you can use the distributive property. Pick up 4x minus 2 and distribute it into all those terms. So I have 1 half x squared times 4x minus 2 minus 3x times 4x minus 2 plus 1 times 4x minus 2. If you use a table, you're going to get these exact terms that I get in this next step. Distribute 3 more times. That gives me 2x cubed minus x squared. I'm distributing a negative 3 here, minus 12x squared plus 6x plus 4x minus 2. Now I'm going to combine my like terms and get 2x cubed minus 13x squared plus 10x minus 2. So if I multiply those two functions together, I get this new polynomial function, 2x cubed minus 13x squared plus 10x minus 2.